Hi, welcome again to A.2 Forces and Momentum, Part 2. This time we'll focus specifically on momentum. So, what is momentum? Well, a loose definition of momentum, that means you can't really write this on your exam, is that momentum is the quantity of motion that an object has. Now, that might sound a little strange, and I'll give you credit. It is very strange. Momentum is sort of an abstract quantity. It's not really something you can see visually, much like you can see velocity or speed. It's very, very different. So, linear momentum is basically the quantity of motion that an object has when moving in a single dimension. It's measured in kilogram times meter times per second, which you would say as kg meters per second. So now let's look at the formula to get a more formal definition of momentum. So this p here is momentum, and this m is mass, and this v is velocity. Now this right here dimensionally is consistent with the units, as m is measured in kilograms and v is measured in meters per second, and you multiply them together. So, looking at this equation, we can derive a more formal definition of momentum. Momentum is a quantity that is directly proportional to the velocity of the object, and it's also directly proportional to the mass. But usually, mass is constant, so we say momentum is directly proportional to velocity. And if you're asked to define this in an exam, what I'd suggest you do is write down this formula P equals mv and state P is momentum, m is mass, and v is velocity. So, because momentum is so abstract, it's a little bit difficult to visualize. So, if you see this photo here, it's of those balls that you know about, the ones that swing from left to right to left to right. And the thing is, when you pull one of these balls out and let it go, it falls and hits this next ball here, and that hits this ball, that hits this ball, and that causes a chain reaction. So that's sort of what momentum is. It's the quantity of motion that that chain reaction has. That's a bit more of a practical way to think about it. So now let's look at some properties of momentum. Momentum, like I said, is quite abstract, but it's still a vector quantity. That means that the initial direction of momentum is given the positive value. So if you look at this photo right down here, this ball here is moving to the right. So we take the right as being positive, and this ball is moving left. So because we saw this ball second, we just take it left as being negative. So that means that we have a negative velocity on this pink ball and a positive velocity on this blue ball. Stationary objects have zero momentum because the velocity is zero, and if we look here, anything times zero is equal to zero. So that's basically the fundamental part of momentum. Now, the main part of that you need to know for IB physics is that the magnitude of momentum is always conserved when no external forces act. So this part here is especially important, the no external forces, because if you apply an external force on something, there's always going to be a reaction from that system that's equal and opposite in magnitude. So momentum will actually increase, and that's something we'll see later. But the conservation of momentum, as it's called, is always correct when there is no external force. That means the momentum before the collision is equal to the momentum after. If we take a look at these two balls, one is traveling with m1 v1 and the other is traveling with m1 negative v2, because this is in the opposite direction. Then they hit and then they travel away. So we'd actually be able to equate the momentum before to the momentum after to find any of these four variables. So let's take a little bit of a deeper look at the conservation of momentum. It's a little bit of an abstract concept, so I think it deserves something a little bit more detailed. So the total linear momentum before a collision is equal to the total linear momentum after the collision. That's the formal definition of the principle. So that just basically means the total momentum before equals the total momentum after. So let's take a look at this trolley right here. So this trolley is moving this way, It weighs 30 kilograms and it's traveling at 2 meters per second. So its momentum, m1v1, is equal to 30 times 2, which is 60. Now let's assume this one is stationary currently. So now when this hits it and it transfers all of its momentum over, we know that this car right here, this cart, whatever you want to call it, has a mass of 22 kilograms and travels at v2. So we equate the 60 here to v2, which then shows us that we have 60 divided by 22 as our velocity, and doing this we get the velocity is 2.73 meters per second in the positive x direction. So that's basically the entire principle of conservation of momentum. It's quite simple algebra if you break it down. So let's get into something that's a little bit more important: impulse. So when there's a net external force, momentum is not conserved, right? So if you remember here, it says when no external forces act, but when there is an external force, the momentum conservation principle does not apply. Now, this change in momentum that happens is called an impulse, and it's represented by this J here. And the impulse is the product of the force applied and the time for which the force is applied. So we can see here that it's called F delta t. So we're just multiplying the force from Newton's second law and multiplying it with the time for which it is applied. So if the force is 5 newtons and I press that and I exert that force for 2 seconds, then the impulse is 5 times 2, which is 10. Impulse has the exact same units as momentum, so it is also measured in kg meters per second. And yeah, so let's take a look at Newton's second law, because that's something I very briefly mentioned earlier when talking about momentum. So let's look at it in more detail. In the first video, part 1, I said that at that point in time we would not be able to put Newton's second law in words. We should just memorize it as F equals ma. But now that we know about momentum, we can create a word definition for Newton's second law. That is, the resultant force on an object is equal to the rate of change of the object's momentum. So in essence, that basically means that the gradient of the momentum time graph is equal to force. So as you can see, F is the same as delta P by delta T, where delta T is the change in momentum. Now, if we rearrange this, we get delta P is equal to F delta T. Now, you might notice something very, very similar. F delta T is the formula for impulse. That's right, so impulse is the change in momentum. So J and delta P mean the exact same thing, and both of them are equal to mass times the final velocity minus mass times the initial velocity, which is once again a restatement of change of momentum. So Newton's second law basically says that force is equal to change in momentum by change in time, which is the exact same thing as mass times acceleration. So now let's take a look at collisions and explosions, which can be quite cool stuff when you see them in movies, but sometimes can also be quite sinister. So if you know what this represents, it's a photo of Hiroshima, which was tragically bombed during the Second World War with a nuke. And that nuke was actually an explosion, something like this over here. And this is what we'll be looking at in terms of a momentum standpoint. So just to give a little bit of context, physics can be very tragic. This is like a TOK sort of side stand, but yeah. Now that we're done with all of that, we can take a look at this thing here. This is a Tsar Bomba, and it's a Soviet nuclear bomb. It's one of the biggest ever built, I think the biggest ever built during World War II. And this works on the principle of conservation of momentum from a mechanical point of view. Not literally the nuclear thing, but what happens when it detonates. So collisions are when moving objects hit and exert a force on each other, right? So if I throw a ball in the air and I throw another ball that after this first ball and they hit each other midair, that's a collision. An explosion is when two or more objects that are initially at rest explode apart. That should not say explore, that should say explode. So when they explode apart, much like a bomb or something like that, a dynamite, that's what an explosion is, right? It splits into many different pieces. That's what an explosion is. So let's take a look at one-dimensional collisions first. One-dimensional collisions usually involve two objects hitting each other on a straight line. So momentum is conserved. So as you can see, this M1 ball here is traveling at speed v1 to the right. This M2 is traveling at speed velocity v2 to the left. So this one we take as positive, this one we take as negative. So if we have mv1 and then we have minus m2v2 as what the initial momentum is. Now when these two hit and bounce apart, we have negative m1v1 plus m2v2, because now this is traveling to the right. Now we can equate these two statements to solve for any variables. So a key thing to realize is that I said these two scenarios up here and down here equal each other, so that implies momentum is conserved. Now let's look at explosions in one dimension. Explosions in one dimension usually involve one stationary object becoming two objects moving away from each other on the line. So if you look at this cannon here, initially it's stationary. It has this sort of cannonball inside it, and it's part of the cannon. But as soon as you light this fuse loaded up with gunpowder and all of that, this sort of explodes away from the cannon, and so this cannonball moves forward. But because of that, this cannon, moves slightly backward at a smaller velocity v. Now the reason for that is the net momentum has to be zero, and the mass of this cannonball is much less than the mass of this big cannon. So we have to have a greater velocity on this for it to equal the negative momentum that's given by this. So big M times v has to equal negative of small m times u. So yeah, the net momentum is zero. Now let's look at inelastic and elastic collisions. In any collision, momentum can always be assumed to be conserved so long as there is no external net force, but kinetic energy is not always conserved. Now, you might be wondering, what is kinetic energy? Well, that's not really something that you need to know right now. We'll cover that in the next topic, 8.3, but we just need to know that right now, if kinetic energy is conserved, the collision is elastic, and if it's not conserved, the collision is inelastic. So in an inelastic collision, the two objects stick together, so it's a sticky collision is what it's called. So as you can see, in an elastic collision, this ball here and this ball here hit each other and then move away. But in an inelastic collision, this ball here hits this ball and then they move in the same direction, sticking together. So if this were an inelastic collision, both of these objects would be either moving left or right, depending on which one is a little bit heavier. And as you can see, this one is actually elastic because they're moving away. So this is called a perfectly elastic collision. It just means that no kinetic energy is lost. In real life, we can never have a perfectly elastic collision, so that's something to keep in mind. That's why you might notice that if you throw a tennis ball on the floor from a certain height, it doesn't bounce up to the same height, because some kinetic energy has been lost. So now let's look at collisions and explosions in 2 dimensions, knowing about inelastic and elastic collisions. So if I have a ball here, this red ball, and I shoot it to the right, and then it hits a stationary blue ball and that shoots downward, then we have something called 2-dimensional momentum. So momentum now has horizontal and vertical components. So the horizontal component of linear momentum is mv cos x, where x is theta 1 or theta 2, depending on which one we're looking at. Vertical component of momentum is mv sine x, where x is equal to 0 or 1. Right, so as you can see on this label, m2 v2 sine theta 2 is the upward momentum that this ball has got from this ball, and m1 v1 sine theta 1 is the downward momentum that this ball has got from the red ball. So it's a little bit weird at first to think that this ball inherits this momentum, but that's what it does. So now let's look at angular velocity. This is a little bit easier. It just means the angle covered per unit time when moving in a circle. So think about if you're walking in a perfect circle, that just means how much of an angle in radians do you walk every second. So angular velocity is this W looking symbol here. It's called omega, and it means omega is equal to theta, which is another Greek symbol. You might have seen it in physics, or sorry, in trigonometry, uh, divided by time. So theta is the angle in radians, so circular measure. I'm sure you've learned about this in math, but if you haven't, it's just an easier way to divide a circle, where a circle is 2 pi radians, which means that 2 pi radians is 360 degrees. Now, you could do all of these calculations in degrees, but it's suggested to do them in radians because it makes it a lot easier. So, yeah, that's basically angular velocity. And it relates to linear velocity in these ways, but it's something that we'll come back to in a little bit. So, just remember, theta is 2 pi r, so that's all you need to know. So you can sometimes substitute W equals 2 pi r by t to find the angular velocity. So let's look at period and frequency, because this is something that's really important when we go back to understanding the other definitions of linear velocity. So period is the time taken to complete one cycle. So as you can see here, it's just time divided by number of oscillations. Frequency is 1 over the period. This just means it's how many oscillations can we complete in a certain period of time. So it's number of oscillations by time. And they have an inverse relationship. That means that frequency is equal to 1 over the period, and the period is equal to 1 over frequency. Now, if we look at W, we can also think that this is theta by t, and we replace this to t by theta, then we can basically write frequency as 2 pi times, we can write this W here as 2 pi f. That's something that's going to become really important in Unit C, but right now it's not so important. So angular displacement is basically the area underneath a angular velocity time graph. So this just means the change in angle in radians as it rotates around a circle. So angular displacement is basically just the displacement, the theta, from here to here. Now this formula here makes a lot more sense. It's just speed equals distance by time written in an angular circular fashion. So let's take a little bit of a look at centripetal force. This is really key to understanding velocity, and it's possibly the most important point of A.2. So centripetal force is when an object in uniform circular motion continuously changes direction, velocity constantly changes, right? Because if an object changes direction constantly, it means that the velocity keeps switching between plus, minus, somewhere in between, something like that, right? So there's an acceleration always. Even though the speed is the same, the linear speed, the velocity changes because the direction changes. This is called a centripetal acceleration, and that centripetal acceleration that causes this change in velocity is perpendicular to the linear velocity. So if we look at this diagram here, the linear velocity is just a straight line tangent to the circle. This sort of string here is going at an angular velocity of omega about the central axis, and it has a centripetal force towards the center of the circle. So there's an acceleration towards the center of the circle according to Newton's second law, F equals ma. So the force is in the same direction as the acceleration. So this force here is called a centripetal force, written as F's, like this, with an abbreviated C and a P. And this centripetal force is the resultant force perpendicular to this velocity provided by another force, and it's required to keep the body in uniform circular motion, so spinning in a circle basically. So this centripetal force is always towards the center of the circle. To calculate it, we can just multiply the mass times the velocity squared divided by the radius. So here the radius is the distance from this point to this point, the velocity is this value here, and the mass will be given in the question. So now we can also write this as mass times radius times angular velocity squared. So now is when we start to take a look at some examples of it and then revisit the definition of angular velocity and linear velocity. So centripetal force can be in many different types and forms. Centripetal force on itself is not a type of force. It's actually supplied by many different forces. For example, in this case, with a satellite orbiting the Earth, the centripetal force is gravity. In this case of a person spinning a hammer in an Olympic fashion, the centripetal force is actually provided by tension. And in this case of a car going around a roundabout, the centripetal force is friction between the cars, the wheels, and the road. So yeah, like I said, centripetal force comes from an acceleration called centripetal acceleration, and this acceleration can be written as v squared, which is linear velocity, squared by the radius of the circle, or as the radius times the angular velocity squared. Now, that said, if we know v squared by r is equal to w squared r, we can derive expressions for v, linear velocity, in terms of angular velocity. So let's go back to this slide right here. We know that velocity is equal to displacement by time, and we know that displacement in a circle is equal to radius times theta, because that's basically the distance around this circle that we cover. So S is the same as r theta. Now we know that r is equal to theta by t. So we have r times theta by t. We take this out, and then we get theta by t is equal to omega. So v equals omega times r. So the linear velocity is equal to the angular velocity times the radius. So now let's look at non-uniform circular motion. These are two formulas that you do not need to memorize, but they're quite useful to know when you think about this. So when there's a changing resultant force, like in a vertical circle, we call this non-uniform circular motion. Now, the only point detailed in the IB Physics syllabus is a vertical circle, so we'll look at this. So at any given point here, gravity acts downwards, but tension always acts towards the center of the circle. That means at some points, centripetal force is provided by tension and gravity, but at other points, centripetal force is only provided by tension. So at this point here, you can see centripetal force is tension minus gravity. And here, centripetal force is actually equal to tension plus gravity. So the maximum tension occurs here when the tension is actually equal to the centripetal force, which is some arrow here, plus this mg, because that acts in the negative direction, and the minimum tension is up here when we have centripetal force minus the weight is equal to the tension. So that's just something that you should be able to derive on an exam. It's not very difficult. It just says that the maximum tension occurs when weight and tension act in the opposite direction. So let's try this question now. An object is moving in a straight line. The force F and a resistive force small f act on the object along the straight line. Both forces act for a time t. What is the rate of change of momentum with time during time t? Alright, so now that you've had some time to try it, let's try it ourselves. So the first key tip is to highlight key words. The object is moving in a straight line. A force F and a resistive force F act on the object along the straight line, so it's in the same direction. So both forces act for a time t. What is the rate of change of momentum with time of the object during time t? So let's first write what the question wants us to find. It wants us to find the rate of change of momentum, which is the same as change of momentum divided by change in time. How do I know this? Well, the rate of change of anything is that thing divided by time. And the rate of change of momentum must mean change of momentum divided by change of time. So yeah, this is what we're asked to find. But notice, this thing right here is given in your data booklet as being equal to F, force. So that just means the rate of change of momentum is force. So what does this mean? It just means we need to find the net force acting on this object, which in this case is big F minus small f, which is option B. So our answer is precisely option B. Thank you so much for watching, and I hope this proved helpful to you.